Hello everyone, welcome to this lecture on residual analysis for the course Stat 3150, Statistical Computing. So in the previous lecture we talked about linear regression and we quickly reviewed simple linear regression. In this lecture the objectives are as follows. So we'll discuss the different assumptions behind linear regression, and after the lecture you should be able to recognize the relative importance of regression assumptions. They're not all as important as the other one. And then being able to interpret residual plots to determine whether the assumptions are likely to be met. So we haven't talked about assumptions yet in the previous lecture. We were really in the simplest setting of simple linear regression, and we were talking about how linear regression subsumes common tests or common statistical procedures like t-tests and ANOVA. So in this lecture we'll talk about residual analysis, which is a general framework that allows us to assess whether the assumptions are met and whether we should change our model. In this lecture, in this course, we'll focus on a graphical approach to residual analysis. In other courses you may see different approaches. You may see approaches based on hypothesis testing. But in this class we'll mostly make graphs, and we'll focus on those graphs. Okay, so multiple linear regression. Let's again get some notation down first. So recall that y is an outcome variable and x1 up to xp are covariates. In multiple linear regression, we have a linear regression equation of the following form. We have the expected value of y conditional on all of the covariate values, x1 up to xp, is equal to beta 0 plus beta 1 x1 all the way up to beta p xp. You may also have seen a slightly different equation. You can also write this in terms of y is equal to beta 0 plus beta 1 x1 dot 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 beta p xp plus epsilon, where epsilon is a random variable that's assumed to be of mean 0 and variance sigma squared. Those two equations are more or less equivalent. You can use either one. I typically prefer the first one just because it generalizes to other models quite directly. We can write this using a shorthand notation using matrices. We can write this as the expected value of y given bold x is equal to beta t times bold x, where beta is a vector of length p plus 1, and it contains all of our coefficients, beta 0 all the way up to beta p, and bold x is a vector of length p plus 1 as well, where the first element is the number 1, and then the next p elements are the p covariates, x1 up to xp. The way we typically estimate the beta, the vector beta of regression coefficients, is through least squares estimation. We won't derive this. I just want to put it out there so that we have it as a reference. But let's assume that we have a random sample of size n. So this means that we have n outcome variables, y1 to yn, and n vectors of covariates, x1 up to xn. And recall, we're assuming that we've measured yi and bold xi on the same sampling unit. Okay, so we'll write y in Blackboard typeface for the vector whose ith element is yi, and similarly for x, Blackboard typeface for the matrix whose ith row is xi, the bold xi. So in other words, we're getting a vector with all of the outcomes and a matrix with all of the covariates, where that matrix is such that each row corresponds to a set of covariates. And once we have that notation, we can write down the least squares estimate beta hat for the regression coefficients, and it's given by the following matrix multiplication. It's x transpose times x inverse, so the inverse of that product, times x transpose times y. So in the background, that's essentially the computation that the function lm is doing. Okay, so once we've found our estimates, once we have the estimates for all of the regression coefficients, we can compute two extra values. So we can compute what we call the fitted values and then the residuals. We'll use the hat notation to indicate that a parameter has been estimated. So for example, beta 0 is the population parameter and beta hat 0 is the estimate. So now let's assume that we have all of our estimates, beta 0 hat, beta 1 hat, all the way up to beta p hat. And for a given observation in our data set, we also have our covariates. So xi1 all the way up to xip. How can we define the fitted values and the residuals? We can define them that way. So yi hat will be the ith fitted value, and we get it by essentially plugging all of these values in the regression equation. So we get beta 0 hat plus beta 1 hat times xi1 plus beta hat p times xip. Or in matrix notation, we just multiply our beta hat by x, and we get all of the fitted values in one shot, in one matrix multiplication. Right, so you can think of this as an estimate of the expected value, essentially. Okay, so once we have our fitted values, we can define the residuals by taking the difference between the observed value yi and the fitted value yi hat. So the residual here we'll call e hat I, and it's going to be equal to this difference. So those are the residuals, and those are the basis of what we call residual analysis. And of course, the whole point is that the fitted values and the residuals can help us understand the fit of our regression model. Is it a good model? Is it a bad model? And it can even tell us or give us hints about how to improve the model. Okay, so that was the notation. Now let's talk about the assumptions of linear regression. I'm going to use the assumptions and the way they're presented in this textbook by Gelman, Hill, and Vehtari from 2020, Regression and Other Stories. And what I really like about this is that they list the assumptions of linear regression in decreasing order of importance. And so the first one is the validity. Is your linear model a valid way to investigate your research question? That should be number one, the first thing you look at. And then representativeness of the data with respect to the population. So is the data you collected representative of your population? And is your linear model accounting for differences between your sample and the population? And so those two are actually not statistical questions at all. They're questions related to the subject matter. So the two most important assumptions are not statistical. But the remaining four are. And we're going to focus on the other four. So number 3 is additivity and linearity. We'll go a little bit about what this means, but essentially it means whether the regression equation is a good description of your data generating mechanism. And then number 4 is the independence of the errors. So independence of your epsilon i's. Then number 5 is equal variance of the errors. One of the assumptions is that they all have the same variance. And then the last assumption is normality of the errors. And you'll see this often. We assume that the epsilons follow a normal distribution. But this is actually the least important assumption. And we typically don't really care about, we don't care too much about whether it holds or not. Okay, so let's go through those assumptions one at a time. So the first, or the most important mathematical assumption is that additivity and linearity holds. And what this means is that this equation for the conditional expectation of y is a good description of how the data is generated. So in plain English, essentially what this means is that changes in the conditional mean of y should be additive and linear with respect to the covariates. And note here that I'm really thinking about conditional means. It means on average. So it's probably the case that life is nonlinear and non-additive, but on average, linearity and additivity can still be very good approximations of that phenomenon. And so we're not necessarily saying that this is what happens for each observation. We're just saying that this is a good description of the average phenomenon. Okay, so how are we going to assess all of those assumptions? Well, we're going to use diagnostic plots, right? So I mentioned at the beginning of the lecture that we're going to use a graphical approach. So we're going to use different types of plots called diagnostic plots to look at whether there's a violation of those assumptions. For simple linear regression, which means there's only one covariate, you can actually plot the outcome against the covariate. So this is the simplest setting, and you can actually see whether linearity is a good assumption or not by using a simple scatter plot. But more generally, what we're going to look at is plots of the outcome against the fitted values, and then plots of the residuals against either the fitted values or the covariates. And I'll note here that in general it's not recommended to plot the outcome against the residuals, and we'll see why later, but it boils down to the fact that we actually expect correlation between the outcome and the residuals. So it's not really informative to look at that plot. Okay, so let's look at a couple examples. First, we'll start with the iron slag data set from the DAAG package. That data set contains 53 observations of iron measurements, and those measurements were obtained using two different methods. One method is chemical, and the other one is magnetic. And the idea is to measure how much agreement there is between those two methods. So first, we'll fit a linear model with magnetic as the outcome and chemical as the covariate. So we get LM of magnetic tilde chemical, comma data equals iron's lag. Next, we can look at a confidence interval, for example. And if we do so, we can see that actually 0 is not included in the confidence interval. But actually 0 is probably not the value that we would be looking at. We're probably more interested in 1. The value 1 would correspond to perfect agreement between the two measurements. And we can see that actually 1 is included in the confidence interval here. Okay, so this is simple linear regression, just one covariate. So we can actually look at a plot of the outcome versus the covariate. And we can check whether the fitted linear trend is a good description of the data. So let's do this. First, I'm plotting a chemical on the x-axis, magnetic on the y-axis. Next, I'm adding a line where the intercept for the line is my estimate of the intercept. So coef fit will give me all of the coefficient estimates. And then I'm taking the first one, corresponding to intercept. And then b equals coef fit bracket 2 specifies the slope of the line that I want to draw on the graph. So if we look at the output here, we can see that indeed the linear line looks like a good description of the data. There's not many large deviations from that linear trend. So at first glance, we don't see any evidence that additivity and linearity doesn't hold. Okay. We can also look at fitted values against the residuals. So I'll be plotting the fitted value on the x-axis, the residuals on the y-axis. And I'm also plotting a horizontal line here. So h equals 0 corresponds to a horizontal line passing through y is equal to 0. And this is what we get. And the reason why we're plotting, we're adding the horizontal line is that we expect no correlation between the fitted values and the residuals if the model holds. So what we're looking at here is a non-uniform distribution of the points along the horizontal axis. And it may not be easy to see, but looks like there may be some slight deviations from this. It almost looks like there's a parabola that could describe the relationship between the points here, but that association is slight. So we'll come back to this. Okay, so the residual plot, as I said, shows evidence of heteroskedasticity in particular, and violation of additivity and linearity. So if I just come back here, heteroskedasticity means unequal variances. And so it looks like the variance for smaller values of the fitted values is lower than the variance for larger values of the fitted values, right? So if I look at the left-hand side of the plot, the range of values is tighter than if I look at the right-hand side of the plot, where it's wider. And so this would be evidence of unequal variance, or heteroskedasticity. Okay, so as a conclusion, it looks like some of the assumptions of the linear model are potentially violated. So some of those assumptions potentially don't hold. Okay, now let's now you have the chance to try this. You can pause the video and try this exercise. So use the dataset mammals from the package mass. And first you need to create a new variable called log_body by using a log transformation on the body size measurement. So once you have that new data set with the new variable, you can fit a linear model of brain by log body. So brain as the outcome and log body as the covariate. And then investigate whether the assumptions hold using the same type of diagnostic plots that we've looked at in the previous example. Okay, I hope you took the time to try it out. So let's look at the solution together. So first of all, I'll note that the mammals dataset contains body and brain size measurements for 62 mammals. So first we'll load the package, library mass, and then we're going to define a data frame called dataset, and that data frame will have that new variable called log body. Here I'm using the transform function. You could do this a number of different ways. But the first argument is the dataset mammals, and then the second argument is the definition of the new variable. So I'm doing log_body is equal to log of body. And here body corresponds to one of the variables in the dataset mammals. Once I have this new dataset, I can fit the model. I get lm brain tilde log body, comma data equals dataset. And then if I look at I can compute the confidence interval and maybe try to interpret it. But first, let's focus on the diagnostic plot. So we'll start with the plot of the covariate on the x-axis and the outcome on the y-axis, and then plot the fitted linear line and see if it's a good description. And if we do this, now we see that the linear fit is not a good description at all. We can see that there's a lot of, it almost looks flat at the beginning, whereas our line is sloping. And then at the very end, there's a lot of large values. And the line is not capturing any of that. So that's evidence of additivity and linearity probably doesn't hold. But let's look at the fitted values against the residuals as well, just to check. And if we do this, we get a similar picture where it's clear that the residuals are not uniformly distributed along the horizontal line. We get essentially the same pattern as we got earlier, but slightly rotated. And so it's clear that something is wrong with the model. But how do we fix this? Well, in this particular case, because we can actually plot the covariate versus the outcome variable, we can see that the relationship actually looks kind of exponential. It's almost flat at the beginning and then it quickly jumps up. So if we log transform the outcome, the relationship should look more linear. So let's try that. So I'm creating again this data set using the transform function. Now I'm defining two variables, so log body, just like before, and log brain, which will be my second transform variable. So I'm also transforming here the outcome. Now if I fit this model of LM of log brain tilde log body, we can again compute the confidence intervals and look at the diagnostic plots. So let's start with the first one. Covariate on the x-axis, outcome on the y-axis, and then the fitted linear line added on top of it. We can see now that actually it's a very good description. So the line is going through most of the points, and there's some random variation below and above that line, but the fit is pretty tight. There's no large values that are very far from the line. And next, let's look at the fitted against the residuals. And now we don't see much evidence of heteroskedasticity. This pattern looks quite uniform. Maybe there's a little bit more variance in the middle, but that's pretty slight. So I would conclude that the residual plot shows little evidence of heteroskedasticity or any model violation whatsoever. So the conclusion would be that the assumptions of the linear model they probably hold here. And so I wouldn't look at further transformations or changes to the model. Okay, so those were two examples. Now, so I just want to point out that a regression model has a life cycle. It's really rare that you will have a data set, decide on a regression model, and then fit it and be done with it. Typically, you need to go through this life cycle right here. So first you do model building, which means choosing the variables in your model. And then model fitting is running the regression. And then next step is understanding the fit, understanding whether your model is a good description of the data. And this is what we're doing here. This is what residual analysis is about. And then once you've generated all those graphs, you can criticize your model and then repeat. Based on the criticisms that you saw from the residual analysis, it gives you ideas about how to change your model, so you just go back to the first step. So you change your model, fit it again, run a new residual analysis, and so on. So regression or data analysis really is typically an iterative process. Okay, so we've focused a lot on the first assumption, or the first mathematical assumption of additivity and linearity. And we talked a little bit about heteroskedasticity. But I want to point out that this is actually a fairly unimportant assumption, having equal variance. If the goal of the model is to do prediction, then accounting for unequal variance will actually improve accuracy. But when the goal is inference, the unequal variance is typically not very important. What I mean by this is that heteroskedasticity does not affect the validity of the confidence intervals. On the other hand, though, accounting for the unequal variance can sometimes lead to more efficient inference, which means that your confidence intervals will be smaller. So if you don't account for it, your confidence intervals will still be valid, but typically wider. Okay. So when is this assumption not met? Well, it's actually it happens quite often, and often it's also a feature of the data. So it's not something that that you can really control. So it's common to have the variance depend on the covariates, for example. And I'm giving an example here. So higher income patients may have more variability in their diet. And so if you're measuring diet somehow as your outcome variable, then you may see a relationship between the variance or the variability in the diet and the income of the patients. How to fix this? We won't really go over much of the details here, but there's something called weighted linear regression that you can use, and we won't discuss this. Or you can also use different standard errors. So for example, you have something called the Eicher-Huber-White standard errors, which I'll mention in the next few slides. And by using those standard errors instead of the typical standard error estimates you get, you can get more robust regression effectively. And regression that accounts for the unequal variance in the errors. And it also turns out that those standard errors can help address some of the issues you get with dependent error terms or dependent epsilons. Okay, so how do we do this? So let's go back to the first example. Here I'm loading the DAAG package, and I'm fitting the same model we had earlier. So magnetic tilde chemical, and then data equals Aaron's lag. Here I'm again computing the confidence intervals. And I'll just point out that we get 0.68 to 1.50, more or less. Okay, now let's use the Eicher-Huber-White standard errors instead of the usual standard errors. And I'll point out that it changes the confidence intervals, but it doesn't change the estimates themselves, right? So the only thing we're changing is the way we estimate the standard errors. And to do so, we can use a couple functions coming from two different packages. The first package is lmtest, and the second package is called sandwich. I know it's a strange name, but sandwich refers to a way of estimating standard errors. It's called the sandwich estimator. Okay, so what we're doing here is computing the confidence intervals using a different function called coef_ci. First argument is still the object fit, but then the second argument is as follows. So it's vcov dot, that's the name of the argument, and then we need to specify the way to estimate those standard errors. And the one that we were interested in, so the Eicher-Huber-White, we can get them by using the function vcov_hc. So if I do vcov_hc of fit, I get my Eicher-Huber-White standard errors, and then I can pass this output to the argument vcov dot. And if you do so, then you get slightly different confidence intervals. For example, the confidence interval for chemical goes from 0.65 to 1.18. So in this case, if I just go back, in this case, the confidence intervals is not necessarily narrower or wider. It's just they're essentially the same, right? So it's a little bit wider, but not by much. Okay, so now it's your turn. So compute robust confidence intervals for the regression model of log brain versus log body. And compare with the usual confidence intervals, so the confidence intervals that we get using the confint function. You can pause the video and give this a try. Okay, I hope you had time to try this out. Here's the solution. So here I'm defining again the same data set we had earlier. I'm using a slightly different function just to show you we can do this in multiple ways. Before I use the transform function, here I'm using the mutate function from the tidyverse. But then so the rest of the code is what we saw earlier. So log brain tilde log body, and then data equals data set. So let's look at the usual confidence intervals first. What we get when we do this, we get about 69 to about 0.81. So that's the usual confidence interval for a log body. Next, we can compute those robust confidence intervals using the same code as before. So remember, we're using the function coef_ci. Then the first argument is the object fit2. And then the second argument is the standard errors that we compute using the vcov_hc of fit2. And when we do this, now we get slightly smaller confidence intervals, but again, they're essentially the same as the ones before. So it turns out that in those examples, even though we saw some evidence of heteroscedasticity for the first data set, the heteroscedasticity is not a big issue. And so even when we use robust confidence intervals, the output is quite similar. But of course, on other data sets, you could see a different behavior. Okay, so this is the last slide. So in summary, residual analysis allows us to evaluate the fit of our model. In other words, how well does the model explain the data set? And we talked about how the most important statistical assumption is additivity and linearity. So in other words, that the regression equation, which is an equation for the conditional expected value, that equation holds. If it doesn't seem to hold, it means you need to change the regression model. So either you transform the variables, or another strategy is to add more covariates. So sometimes it just means that there's some variability that your covariates are not capturing, and so you need to add more covariates in your model. We briefly talked about equal variance, and we saw how to fix this using different standard errors, but that assumption is not as important. And the other assumptions are even less important, and in particular, non-normality of the errors is rarely a problem. And so for that reason, I don't even recommend looking at that assumption. We'll typically ignore it. Okay, so this is it for the residual analysis slides. In the next lecture, we'll go back to resampling methods, and we'll discuss how Bootstrap can be used for linear regression.